Welcome to Unit 18, video number 1. This video will focus on how to assign oxidation numbers to elements in compounds. By the end of this video, you should understand the difference between oxidation and reduction, and be able to assign oxidation numbers to elements in a compound. Let's start by defining the terms oxidation and reduction. This is why we're learning to assign oxidation numbers, so let's start there. An oxidation and reduction reaction is a reaction in which one or more electrons are transferred. We often refer to these as redox reactions. We can't have a reaction where oxidation occurs without also having reduction occurring. So which is which? Oxidation is the loss of electrons, whereas reduction is the gain of electrons. So in other words, if one element is losing electrons, another element must be gaining electrons in a redox reaction. Again, you can't have one without the other. A useful mnemonic to help you remember the difference between oxidation and reduction is oil rig, or oxidation is loss, oil, reduction is gain, rig, oil rig. Let's take a look at an example. This is a reaction we've seen before. Here we have elemental sodium and elemental chlorine, meaning neither one are ions. They're both neutral, so they have zero charges. However, when they react, we end up with NaCl. As we know, this is the combination of a positive sodium ion and a negative chloride ion. This means that the charges of the elements must have changed. In other words, electrons must have been transferred. So, take sodium, for example. In order to go from a charge of 0 to positive 1, it must have lost an electron. Recall that electrons are negative, so 0 minus negative 1 is positive 1. On the other hand, in order for chlorine to go from 0 to negative 1, it must have gained an electron. Therefore, in this example, sodium lost an electron and chlorine gained that electron, making sodium the thing that was oxidized and chlorine the thing that was reduced. Let's take a look at another example. Here we have neutral zinc and copper 2+. Zinc has a charge of 0, copper 2+ has a charge of 2+. If we look at the other side of the equation, we see that zinc has a charge of 2+ and copper has a charge of 0. In order for zinc to have gone from a charge of 0 to positive 2, it must have lost 2 electrons, meaning that zinc was oxidized. Copper, on the other hand, must have gained 2 electrons to go from a charge of positive 2 to 0. So copper 2+ was reduced. Again, our electrons were transferred from zinc to copper. So how do we determine what species was oxidized and what species was reduced? So clearly in the last two examples, we needed to know the oxidation states of each element in the compounds. The oxidation state is essentially the charge of the atoms in the compounds. They're often also called oxidation numbers. Many of these are very easy to determine. Some are a little bit more challenging.
So let's take a look at the rules for assigning oxidation numbers to elements in compounds. The first two rules we've already seen from the previous examples. First, we saw that uncombined or diatomic elements have an oxidation state of 0. In other words, elements that are not ions or elements that are not combined with anything else have a charge or an oxidation state of 0. Likewise, monatomic ions that aren't in a compound have an oxidation state that is the same as their charge. Na+ has an oxidation state of positive 1. S2- has an oxidation state of negative 2. From here, there are a couple things that need to be memorized. So many elements' oxidation states just correspond to their place on the periodic table. For example, you should memorize that group 1 elements have an oxidation state of +1, and group 2 elements have an oxidation state of +2. You probably already have this memorized from previous information. Likewise, you should memorize that aluminum is always +3, fluorine is always -1, hydrogen is always +1, and oxygen is always -2. These will always be the oxidation states of these elements when they're in a compound. So how do we figure out the things that don't have rules? Essentially, it's by process of elimination. We know that for neutral compounds, the oxidation numbers of all the elements in the compound have to add up to 0. Likewise, for polyatomic ions, the oxidation number must add up to the charge on the polyatomic ion. In other words, for something like nitrate, NO3-, the overall oxidation numbers must add up to -1. For sulfate, SO4-2-, the overall oxidation numbers must add up to -2.
Let's try to apply these rules to a real compound. When doing so, we always want to start with what we know. In other words, start with the things you have a rule for. So we have a rule for hydrogen. Hydrogen has an oxidation state of +1. We also have a rule for oxygen. Oxygen has an oxidation state of -2. Then from there, we want to figure out the rest, which in this case is sulfur. We know that this entire compound has to add up to 0 because it's a neutral compound. So let's see what sulfur must be. Since there are 2 hydrogens, the total contribution from hydrogen is +2. Since there are 4 oxygens, the total contribution from oxygen is -8. Therefore, we need to ask ourselves, what must sulfur be in order to make this compound add up to 0? Since we have a -8 and a +2, right now we have an overall charge of -6. Therefore, sulfur must be +6 because +6 and -6 equals 0. So to review, in this example, hydrogen has an oxidation state of +1, sulfur has an oxidation state of +6, and oxygen has an oxidation state of -2.
Let's do some more examples together. Starting with SF6, we want to start with what we know and figure out what we don't know. So we have a rule for fluoride. Fluoride, we know, is always -1. Therefore, the oxidation state of fluorine or fluoride is -1. However, in this case, we have 6 of these, giving us an overall negative charge of -6. Since the compound must add up to 0, this means sulfur must be +6. Again, we know the compound adds up to 0 because it's a neutral compound. There's no charge indicated. Moving on to the next example, NO3-, we again want to start with what we know. In this case, oxygen is always -2. We have a rule that states that. So oxygen is done. Its oxidation state is -2. However, we have 3 of these, giving us an overall negative charge of -6. In this case, we want the entire compound to add up to -1, since it's a polyatomic ion with a -1 charge. This means that the charge on nitrogen must be +5, since +5 plus -6 equals -1. Pause the video here and see if you can figure out the last compound. Welcome back. In this case, you should have applied the rule for oxygen, which tells us that oxygen has an oxidation state of -2. Then we can apply the rule for sodium, since it's a group 1 metal, We know that it always has a charge of +1 because all group 1 elements have a charge of +1. And then finally, by process of elimination, chromium must be +6 because that will what will allow the entire compound to add up to 0. This brings us to the end of the oxidation number video. In this video, we learned that oxidation was the loss of electrons, whereas reduction is the gain of electrons. Remember, oil rig. Oxidation is loss, reduction is gain. We also learned how to assign oxidation numbers to elements in compounds. In the next video, we'll use this skill to determine what elements were oxidized and what elements were reduced in various compounds.